Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. This is the second of the foundational videos for the Smith chart series. In the last video I covered resistance versus conductance and impedance versus admittance, as well as how to eliminate the reactive part of an impedance. Now, because Smith charts are all about transmission lines and impedances and admittances associated with them, I need to spend some time going over stuff related to transmission lines. If you're not aware of these facts, using the Smith chart will end up as a dead end for you, and I don't want that to be for the way it comes out for you. Now, don't worry, the math associated with what we're going to be covering is simple, straightforward math. First, we need to be talking about transmission lines, velocity factor, and the electrical length of a transmission line. Then we need to spend a brief time talking about how impedance can change along a transmission line, and at the same time the SWR isn't changing. If you find this video helpful, please click on the like and subscribe to the channel. So let's dive into some transmission line stuff. An important part of the fundamentals that you need to be aware of is the reality that electricity does not travel at the speed of light through a transmission line. It travels at some speed which is some fraction of the speed of light. This fraction is referred to as the velocity factor of the transmission line. Velocity factor is a dimensionless entity that simply defines the percentage of the speed of light that an AC signal will travel down the transmission line. Now, the surprising thing about this is that the velocity factor of a transmission line is almost entirely a factor of the dielectric constant of the insulation used in building the transmission line, which the dielectric constant is represented by this funky letter epsilon. Now consider RG58, which is 50 ohm coax, RG59, which is 75 ohm coax, RG8, which is 52 ohm coax, all constructed with the same insulation, polyethylene, all have the same velocity factor. So for instance, polyethylene has a dielectric coefficient of 2.3. So then the velocity factor here is 100% divided by the square root of 2.3, which is the same as 100 divided by 1.5166, which turns out to be 65.94%. Which, by the way, they round up and they say that the velocity factor of your coax that is built with polyethylene will have a velocity factor of 66%. All right, so now let's relate this whole concept of the speed that a signal travels down a transmission line to the electrical length of the transmission line. So let's picture this in very real terms. Here I have this lovely ball. I stole it from my dog. And we have a metronome going here. Okay, so oscillation, this ball is oscillating. Bump, bump. It's just up and down. This is like the voltage on the output of your transmitter. Now, here's your ball. Do-doom, do-doom. It's oscillating. The frequency at which it reaches this lowest point is not changing. Now, suppose we were to give this ball some horizontal component of its movement. Right now, it's all vertical. It's not going anywhere. Now, if it goes very slow, now notice as I go, how far apart where it hits the bottom is. Nice and slow. Here we go. Notice how close together that is. Now, take the same ball, same frequency. Now, let's move it a lot faster. Ready? Well, I got a little carried away, I guess. But you notice, when it was moving faster horizontally, the distance between where the ball came down to where it came down the next time was further apart. When I was moving more slowly, they were closer together. So now if we envision that the RF in terms of oscillation of the voltage is like the vertical position of our ball. Now, the speed at which this signal, this voltage, is allowed to to travel down the transmission line is determined by the velocity factor. And so here you are, you got this oscillating voltage, and the higher the velocity factor, the closer that it is traveling to the speed of light, the further apart those dips are going to be. On the other hand, if it's traveling more slowly, then they're going to be closer together. The frequency of the oscillation isn't changing, but the velocity of the ball, of the signal down the transmission line is changing as a result of this velocity factor of the transmission line. Now, to calculate, let's calculate the wavelength of a signal in free space. Now, the wavelength of a signal in free space, which is wavelength is represented by the Greek letter lambda, is equal to the speed that the wave is traveling, or in this case, the speed of light, divided by the frequency in hertz. So if you think about this, this is speed. So let's say it's in feet per second, and we're dividing by cycles per second. This is the same thing as feet per second times seconds per cycle. And you see the seconds go out, and we end up with feet per cycle, which gives us the wavelength. Now, this is the speed of light, that's the frequency. So let's take a particular frequency and calculate its wavelength in free space. We know that the speed of light in free space is approximately equal to 11,802.9 mega inches, million inches per second. All right? And let's say that we're interested in what is the wavelength in free space of 146 megahertz signal. So let's set F equal to 146 mega cycles per second. In other words, megahertz. So we end up with 11,802.9 mega divided by 146 mega. The mega on the top and the mega on the bottom cancel each other out, so we end up with inches, which comes out to 80.5 56.84 inches. Okay, so let's just remember this. Let's write this up here on the top here. So lambda, we'll put this in FS, free space, is equal to 80.84 inches. Okay, great. I'm going to leave the C here because we're going to need that. Now we have a piece of coax. We have a piece of coax that has a velocity factor of 66, which means 66%. That means that the speed at which the signal is going to be traveling down the coax is 66% of the speed that it would travel in free space. So we would say then the speed in the coax is equal to the speed in free space, and I'm going to keep my consistency here, speed in free space and then we're going to multiply this by 0.66 because it's 66% of this. So that ends up giving us 11,802.9 times 0.66, which comes out to be 7,789.9 mega inches per second. So that is how fast the signal is traveling down our coax that has a velocity factor of 66 or 66%. So let's go back to this calculation. We want to know what is the wavelength of the signal traveling down our coax. Well, that's this speed here, because this is the speed of travel, which is 7789.9, speed of travel, mega inches per second, divided by the frequency, which is 146 mega cycles per second. So the megas cancel out. And now we get lambda, or the wavelength in this coax, is 53.36 inches. So lambda in our coax is 53.36. Wow, look at the difference. In free space, it's 80.84. In our coax, it's 53.36. So our piece of coax that is 53.36 inches long is referred to as being, electrically speaking, one wavelength long. So what does that mean in terms of the signal traveling down the coax? Well, that's a good question. What that means is that if we have this piece of coax here, and it is 53.36 inches long, it has a velocity factor of 66, and we have a signal going in this side. We have a signal coming out this side. What we see is the signal, because it's electrically one wavelength long, that means that this signal going in here is in phase with the signal coming out here. When this signal's traveling up this way, well, guess what? The very next thing that's happening here is it's traveling up. When this signal is traveling down on this side, this signal's traveling down. So if this signal at a particular point in time is at 0 volts, this signal will be at exactly 0 volts. If this signal is at some peak, maybe 10 volts, then this side is going to be at exactly 10 volts because they are electrically in phase. It's an electrical one wavelength. Well, what would happen if we were to take our coax and cut it in half? Well, we would now be 180 degrees, 1/2 wavelength, gives us 180 degree phase shift. What that means is, here's this signal on its way up, but at the end of the coax, if we're looking here, it's on its way down. So when this signal here reaches its peak at 10 volts, this signal here will reach its minimum at minus 10 volts. So they are doing one of these things, back and forth and back and forth. Well, what happens then if we take this and we cut it in half again? 1/4 wavelength gives us 90 degree phase shift. That means that when this is at its minimum, the voltage at this end of that piece of cut coax is at its maximum. Or it could be so when this is at 0 volts, like we show here, this will be at the peak, or it could be here because it could be this 0 volts. It's 90 degrees out of phase. So when this is at its 0 point, this could be either at its minimum or its maximum, depending upon where we are in the sine wave along the way. Now, this fact is very important if you want to get specific phasing of signals, because you could use, just by way of example, and they do this in one kind of duplexer. This piece of coax is 1/2 wavelength long. Now that means it's 180 degrees out of phase. We have a signal here like this. The signal coming out of here is like this. And then they have a second piece of coax that is 1 wavelength long. The signal here is doing this. The signal here is doing this. They connect these two guys together. This one is trying to go up. This one is doing exactly the opposite. And what you end up with is nothing. They do that in order to eliminate a particular frequency of signal. Now, not only does the voltages change, the phase of the voltages change with this change in the velocity factor, the change in the length of the coaxes, but the impedance changes as the coax gets shorter and longer as the velocity factor changes. So for this reason, we can also use changes in coax length and specific velocity factors and so on to create impedance changes in order to transform from one impedance to another. And that's exactly what we're going to be discussing next. Well, this piece of the foundations has to do with how the impedance changes as you move along a transmission line. Now, the reason why this kind of puzzles us is because we tend to think in terms of DC. If I put a 10 ohm resistor over here, a perfect 10 ohm resistor on a 50 ohm piece of coax, we expect to go out on the other end with our digital voltmeter and measure 10 ohms on this end looking back through there. And that would be true with DC. However, RF is really weird stuff. The reality is that the only place along the transmission line that we will see this perfect 10 ohms is at every half wavelength point. At exactly 1/4 wavelength, here's a surprising one for you, at exactly 1/4 wavelength, electrical length by the way, remember, taking consideration velocity factor and all that, at 1/4 wavelength along that transmission line, our perfect and wonderful 10 ohm load will look like a 250 ohm load with no reactive component, just 250 ohms. But that's 25 times greater at the far end of this 1/4 wavelength than it is at our perfect resistor. I told you it was weird. The reality is the impedance changes in such a way that the SWR remains constant. You see, in our mind, we think, well, if the impedance is going to change, well, then the SWR is going to change too. Well, like I said, it doesn't. It just changes in such a way that the SWR doesn't change, but the impedance does. And it's a very complicated mathematical relationship involving complex numbers and all this mess. I'm not even going to try to go there. The good news is that the Smith chart does all of this for us. So we don't have to even get close to that complex math. We just have to know that it takes care of all this and it indeed works. So what can we do with that? Well, using the Smith chart, we can plot the impedance and then figure out how long of a piece of coax that we need to transform that impedance into something that we want. And that's exactly what we do when we create a stub match at a particular frequency. Or let's say we have an antenna up in the air, and here we have our antenna up in the air, and we have this feed line coming down to our shack. We don't really want to go up here and measure the impedance of this antenna, but we want to know what the impedance of our antenna is. Well, we know the length of coax that we have here. We know the velocity factor of that coax. So now we can look in at the end of this coax, measure the impedance of the entire system up to the antenna. We can plot this impedance on our Smith chart, and then using the Smith chart, we can back up using the Smith chart. We can back up all the way to the antenna and read right off the Smith chart what the impedance of that antenna is. And all of this because the Smith chart does the impedance transformations for us. Now, let me show you a quick demonstration of this using my purposely poor load. All right, I'd like to introduce you to my not so wonderful load, specifically made so that it would be a mismatch. That is a 33 ohm carbon composition resistor in a series with some kind of coil I just wound up. And so now what we're going to do is a demonstration as to what this impedance looks like, and then we're going to put this same one at the end of a piece of coax, and then you will see how the impedance changes, but the SWR does not. So now my VNA has been calibrated right to here, and I've connected up my load here. Now let's see what the SWR and the impedance look like. So here we are with the vector network analyzer, and we have it set for 100 megahertz, and this is the SWR at 100 megahertz. So 100 megahertz, you see it's right here, and the SWR is 4.98 to 1. So now let's take a look at the impedance. To do that, we're going to change format over to the Smith chart, and we're going to use impedance here. So here's our little marker here. This is the Smith chart. Here's our little marker at 100 megahertz. And you notice it says 74.88 ohms plus J106.3. All right, now let's see what happens when we put this extra piece of coax in place. So now I have this lovely piece of coax. It is approximately 0.3 wavelengths long, electrically speaking, and we're going to place that in between the vector network analyzer and our lovely load. And so here it is. The vector network analyzer is connected to this end, and we go all the way around, and our lovely load is connected to this end. So let's take a look and see what the impedance and the SWR is. And so here we are looking at the impedance. This is the Smith chart here on the vector network analyzer. You'll notice that the impedance here at 100 megahertz is now 10.07 ohms plus 1.17 ohms. Very, very different than what we saw before, but let's take a look at the SWR. Look at that, 4.97 to 1. That is just about exactly the same number. So even with the addition of the piece of coax, the SWR clearly did not change, but yet the impedance very clearly and very dramatically changed with the addition of the coax. If I had used a longer or a shorter piece of coax, the change in impedance would have been different, but the SWR would have remained the same nonetheless. So that is our little demonstration of how impedance changes with the addition of coax in your system. So there you have it. The basics of transmission line stuff that you need to know to effectively use the Smith chart. If you found this video helpful, please click on the like and subscribe. The Smith chart is actually all about the reflection coefficient of a transmission line. This is what doesn't change as we move along the transmission line, and that's what makes it so the SWR doesn't change, even though the impedance actually does change. Reflection coefficient has two mathematically related cousins, return loss and VSWR, or what we usually just say is SWR. Because the Smith chart is all about the reflection coefficient, the next video in this series is all about briefly talking about the reflection coefficient and its two cousins. In the meanwhile, thank you so much for watching. Toodle-oots.